Look around you right now. The chair you're sitting on, the light coming through your window, the phone or screen you're staring at. It all feels completely real, doesn't it? Solid, tangible, undeniable. But what if none of it is? What if everything, the table, the air, your own hands, the stars in the night sky, is nothing more than an incredibly advanced computer program? A simulation so perfect, so seamless, that not a single living thing inside it has ever been able to tell the difference? That is the simulation theory. And before you roll your eyes and call it science fiction, here's something you need to know. Some of the most brilliant minds on the planet, physicists, philosophers, mathematicians, and yes, tech billionaires, believe there is a very real chance this is actually true. In this video, we're going to go deep. We're going to start from the beginning, what this theory actually is, where it came from, and why it suddenly exploded into mainstream conversation. Then we're going to follow the evidence. The mathematics, the quantum physics, the strange anomalies in reality that science still can't fully explain. We're going to meet the philosophers who built the logical argument that shook the academic world, and the scientists who are right now designing experiments to try to detect the edges of our reality. And at the end, we're going to ask the question that really keeps people up at night. If this is true, what does that mean for everything we think we know about life, death, consciousness, and what it means to exist? Buckle up, because by the time this is over, you may never look at the world the same way again. Let's start with the basics, because this idea is often misunderstood. The simulation theory, in its most straightforward form, proposes that what we call reality is not a physical universe at all. Instead, it is a computational simulation. A program running on some kind of unimaginably powerful computer, designed and operated by an intelligence far more advanced than anything we know. Think about video games. In 1972, Pong was 2 paddles and a dot. In the 1990s, we had blocky 3D worlds. In 2024, we have games so visually realistic that footage from them is regularly mistaken for real life. We went from a bouncing square to photorealistic sunsets in about 50 years. Now zoom out, way out. Imagine that trend continued for another 1,000 years, or 1,000,000. The civilizations that might exist then, if they still exist at all, would have computational power that makes our best supercomputers look like an abacus. And if they have that kind of power, what would they do with it? Among other things, they might run simulations, detailed ones, with billions of simulated beings inside who have no idea they're in a program. The simulation theory asks, what if that already happened? What if we are those beings? Sounds like the plot of a movie. In fact, it literally was the plot of a movie. But the idea itself, the philosophical and scientific version of it, has roots going back centuries. Descartes, in the 1600s, famously asked whether an evil demon could be deceiving him into thinking the world was real. The Hindu concept of Maya describes reality as an illusion. Even Plato's allegory of the cave suggested that what we perceive as real might be nothing more than shadows on a wall. What changed recently is that we now have a specific, technical, and surprisingly rigorous argument for why this might actually be true, and the math behind it is hard to dismiss. For most of its modern history, the simulation theory was something discussed quietly in academic philosophy departments and the kind of late-night conversations that only happen after a certain number of hours studying theoretical physics. Then 2 things happened almost simultaneously that changed everything. The first was The Matrix. In 1999, the Wachowskis released a film that took the abstract idea of simulated reality and turned it into something visceral, visual, and deeply unsettling. Neo is living a perfectly normal life, and then he discovers that everything he has ever experienced is a computer-generated illusion. The film became a cultural landmark not because it was fun, though it absolutely was, but because it planted a seed. After watching it, millions of people walked out of theaters and thought, even if just for a moment, but what if? The second thing was a 2003 paper by Oxford philosopher Nick Bostrom titled, "Are You Living in a Computer Simulation?" It was published in a serious academic journal, and it presented what became known as the simulation argument, a logical trilemma that we'll get into in detail later. But the short version is this: Bostrom showed that at least one of 3 things must be true, and one of those things is that we are almost certainly living in a simulation right now. Those 2 cultural moments, one from Hollywood, one from Oxford, put the idea on the map. But then Elon Musk came along and poured gasoline on the fire. At a tech conference in 2016, Musk was asked about simulation theory. His answer was casual, confident, and terrifying in its matter-of-factness. He said, "The odds that we're in base reality is 1 in billions." He argued that given the pace of video game development, from Pong to photorealism in 4 decades, a sufficiently advanced civilization could create simulations indistinguishable from reality. And if simulations are possible, then there are potentially billions of simulated realities for every one base reality, which means the probability of existing in the base reality approaches 0. Musk wasn't the only tech figure to weigh in. Sam Altman, Riz Ahmed, and dozens of Silicon Valley insiders have spoken about the theory. There are reportedly people in the tech world who are quietly funding research into how to break out of the simulation. Some of the people building our actual reality, the internet, AI, virtual worlds, genuinely believe they might be living inside one. That's not nothing. Here's the thing, it would be easy to dismiss all of this as philosophical navel-gazing or tech bro eccentricity. Except that the people taking it seriously aren't just podcasters and Twitter personalities. They're people like Neil deGrasse Tyson, who said the likelihood that the universe is a simulation is very high. They're theoretical physicists at MIT and Princeton. They're mathematicians who study the deep structure of physical law. And their reason for taking it seriously isn't vibes. It's the math. Because when you look at the universe at its most fundamental level, not the trees and the oceans and the galaxies, but the actual bedrock of physical reality, it starts to look disturbingly like code. That's where we're going next. If you wanted to build a simulation, one of the first things you'd have to do is decide on your resolution. You can't simulate infinite detail, no computer can. You'd have to pick a minimum unit, a smallest possible thing. Below that threshold, nothing exists. Here's what's wild. Our universe has exactly that. It's called the Planck length. It's approximately 1.6 times 10 to the power of negative 35 meters. Written out, that's 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Below the scale, the very concepts of space and distance stop making sense. Why would nature have a minimum resolution? If the universe were truly continuous and infinite in its detail, there would be no smallest unit. But there is. And to some physicists that looks exactly like a grid. Pixel size. The resolution limit of a simulation. There's also a speed limit, the speed of light. In any computer system, there's a maximum processing speed. Information can only travel so fast. In our universe, nothing travels faster than light. To a simulation theorist, that speed limit isn't just a physical law, it's a computational constraint. The maximum data transfer rate of the system. And then there's quantum mechanics. At the subatomic level, nature doesn't work the way we'd expect. It doesn't track every particle in continuous, perfect detail. Instead, physical properties like position and momentum are described by probabilities. Fuzzy clouds of possibility that only decide what they are when something measures them. That sounds exactly like what a simulation would do. Why waste processing power rendering the precise position of every subatomic particle in a room no one is looking at? Render it approximately probabilistically, and only resolve it into specific values when something interacts with it. Efficiency. Just like a video game that only renders the part of the world the player is currently looking at. Now here's something that should genuinely give you pause. Our universe runs on about 24 fundamental constants. Numbers like the gravitational constant, the mass of the electron, the strength of the electromagnetic force, the cosmological constant that governs the expansion of space. These are the dials of reality, the specific settings that determine what kind of universe we get. And they are set with terrifying precision. If the gravitational constant were just slightly stronger, the universe would have collapsed back on itself seconds after the Big Bang. Slightly weaker, and matter would have never clumped together into stars and galaxies. If the electromagnetic force were slightly different, atoms couldn't form stable molecules, and chemistry, the basis of all life, would be impossible. Physicists have calculated that if you vary any of these constants even by a fraction of a percent in most cases, you get a dead universe. No stars, no planets, no atoms, no life. Nothing. This is called the fine-tuning problem. And it is one of the most uncomfortable problems in all of physics. Why are the constants set exactly as they are? Why does the universe seem to have been precisely calibrated to allow the existence of complexity, life, and observers? There are a few possible answers. Some point to the multiverse, the idea that there are infinite universes with different constants, and we naturally find ourselves in one compatible with our existence. Others point to God. But the simulation theorist has a much simpler answer. Someone set the dials. Programmer. Someone who decided the settings before hitting run. The fine-tuning isn't mysterious at all. If you're running a simulation, of course you'd configure it to produce something interesting. One of the most radical ideas in modern physics comes from the late John Archibald Wheeler, one of the most important physicists of the 20th century, the man who coined the term black hole. In his later years, Wheeler became obsessed with a question. What is the universe fundamentally made of? His answer, information. He called it from bit. The idea is that every particle, every field, every force in the universe, everything physical, derives its existence from binary choices, from yes or no questions, from bits. Reality, at its deepest level, is not made of matter or energy. It is made of information. This sounds abstract until you realize what it implies. If reality is information at its base, if the universe is fundamentally computational, then the distinction between a real universe and a simulated one becomes blurry, maybe non-existent. Other physicists have pushed this further. Max Tegmark at MIT has proposed that the universe doesn't just happen to be describable by mathematics. The universe is mathematics, a mathematical structure that exists independently and contains observers, us, within it. If Tegmark is right, then asking whether we're in a simulation may be asking the wrong question entirely. We may be in something that has always been, at its core, a pattern of abstract information, which, from the inside, would look exactly like what we see when we look around. If there is one experiment in the history of science that most directly suggests we might be living in a simulation, it is the double-slit experiment. And if you've heard of it before, I promise we're going to go deeper than you have before. Here's the setup. You fire particles, say electrons, one at a time at a barrier with two narrow slits. Behind the barrier, there's a detector screen that records where each electron lands. If electrons are simple particles, little billiard balls, each one should go through one slit or the other and land in a predictable spot. You'd expect to see two bands on the screen. But that's not what happens. When you fire many electrons and don't watch which slit they go through, you get an interference pattern, a series of alternating light and dark bands, exactly what you'd see if waves were going through both slits simultaneously and interfering with each other. The electron somehow goes through both slits at the same time. It behaves like a wave spread across space, interfering with itself. Strange. But wait, it gets stranger. What if you set up a detector to watch which slit each electron actually goes through? The moment you do that, the moment the electron is observed, everything changes. The interference pattern disappears. The electrons start behaving like ordinary particles again, going through one slit or the other, leaving two simple bands. The act of observation changes the outcome, not because the detector physically disturbs the electron. Physicists have designed experiments to rule that out. The change happens because of the measurement itself, because information about the electron's path becomes available. The universe behaves differently when it's being watched. Now think about that from a simulation standpoint. Why would reality work this way? Why would a particle be in a superposition of states, essentially be undefined until something looks at it? The answer in a simulation context is obvious, because rendering every detail of reality at all times is computationally expensive. So the system only resolves things into definite states when necessary, when an observation is made. The rest of the time, it exists as a probability distribution, as compressed data waiting to be unpacked. It's lazy rendering, and our universe appears to do exactly that. What we just described has a technical name: the collapse of the wave function. Before observation, a quantum system exists in a superposition, a blend of all possible states. When it's observed, the wave function collapses into one definite outcome. This has been one of the most debated phenomena in physics for 100 years. The Copenhagen interpretation, the standard textbook version, essentially says, don't ask what's happening before measurement, because the question doesn't have a meaningful answer. The particle doesn't have a definite position until it's measured. That's just how reality works. But why? No one has a satisfying physical explanation for why observation would affect the state of a particle. The math works perfectly. The predictions are the most accurate in the history of science. But the mechanism, the why, remains deeply mysterious. Unless you assume that reality is a simulation that renders detail on demand. In that case, there's no mystery at all. The particle doesn't have a definite state before observation because there is no state to have, just a probability distribution, a compressed description of what the state might be if someone were to look. When someone looks, the system computes a specific outcome and presents it. Wave function collapsed. Screen rendered. Reality delivered. Is not a metaphor. The mathematical structure of quantum mechanics maps almost perfectly onto the structure of information processing. Some physicists, and this is not a fringe position anymore, believe that quantum mechanics is not just described by information theory. They believe quantum mechanics is information theory. There's one more quantum phenomenon that fits uncomfortably well into the simulation framework, and it's possibly the strangest thing in all of physics. Quantum entanglement. When two particles become entangled, they share a quantum state. Measure one particle and you instantly know something about the other, no matter how far apart they are. Not after a delay. Instantly. Einstein called this spooky action at a distance and was convinced it couldn't be real. He thought it meant quantum mechanics must be incomplete. He was wrong. Experiments have confirmed entanglement beyond any doubt. Particles genuinely do share states across arbitrary distances, and measuring one does instantly affect our knowledge of the other. Now, this doesn't violate special relativity in the classical sense. You can't use entanglement to send information faster than light. But it does imply something deeply weird, that in some sense, the two particles are not really separate. They are connected by something that doesn't care about the distance between them. In a simulated universe, this is not mysterious at all. Two entangled particles aren't really communicating across space. They're two variables in the same program that share a linked state. When you query one variable, the system returns a value and simultaneously updates the linked variable. There's no signal traveling between them because they're not separate objects in physical space. They're correlated entries in the same database. Spooky? Sure. But only if you assume reality is a physical thing. If it's a computation, it's just good programming. Let's step away from the laboratory for a moment and talk about something more personal. Most people have experienced déjà vu, that uncanny, disorienting sensation that you've lived through this exact moment before. You're in a completely new place, having a conversation you've never had, and yet something in your brain screams that this is familiar, that this already happened. Neuroscience has explanations. Memory misfires. Familiarity signals firing out of sequence. The brain creating a false sense of recognition. These are real, plausible mechanisms. But here's the interesting part. In the Matrix movies, déjà vu is explicitly described as a glitch in the simulation. A sign that something has been changed in the program. And while that's fiction, the framing raises a question worth sitting with. What if some experiences that we chalk up to brain quirks are actually something else? Artifacts, hiccups, moments where the rendering stutters. Then there are synchronicities, those moments of meaningful coincidence that feel too perfect to be random. You think of a friend you haven't spoken to in years, and they call you that same afternoon. You're struggling with a problem, and you happen to open a book to the exact page that addresses it. Jung called these events synchronicities and believed they revealed a deep connection between the inner world and the outer world. Science dismisses most of this as pattern recognition. Our brains are wired to find meaning, and they find it even where none exists. That's probably mostly true. But the simulation framing offers a different lens. What if the program of reality occasionally produces outputs that feel more connected, more meaningful, more coordinated than random chance would predict? not because of mysticism, but because of code. Now we get into genuinely weird territory. The Mandela effect, named after a peculiar phenomenon where a large number of people share the same false memory, has become one of the most discussed concepts on the internet over the past decade. And while psychologists have clear explanations for it, the phenomenon itself is strange enough to deserve a close look. Here's the origin. Nelson Mandela died in December 2013. That's a historical fact. But a surprisingly large number of people, not a handful but thousands, have very clear, detailed memories of Mandela dying in prison in the 1980s. They remember news coverage. They remember speeches. They remember where they were when they heard. These aren't people who are confused or uninformed. They are people with vivid, confident, specific memories of something that did not happen. There are other examples. Vast numbers of people remember the Monopoly man wearing a monocle. He never did. People remember the Berenstain Bears being spelled Berenstein. People remember a specific scene in a film that doesn't exist in any version of that film. The logo of a brand they grew up with, different from how it actually appeared. The scientific explanation is solid. Memory is constructive, not reproductive. We don't record events like cameras. We reconstruct them every time we recall them. And those reconstructions are influenced by suggestion, expectation, and social reinforcement. False memories are normal, and shared false memories happen when groups of people are exposed to similar cultural cues. That's almost certainly the correct explanation for most cases. But the Mandela effect became a cultural phenomenon because it gave people a framework for that deeply unsettling feeling that something is slightly off. That reality doesn't quite match the way you remember it. And the simulation theory offers a dark alternative. What if some of these aren't false memories? What if some of them are correct memories of a previous version of the simulation, one that was patched, updated, or reset? Probably not. But the possibility that we can't fully rule it out is exactly why this stuff keeps people up at night. We talked about fine-tuning earlier, but there are specific numbers in physics that take the suspiciously convenient quality to a whole other level. Consider the cosmological constant, the value that governs the rate of expansion of the universe. Its measured value is almost exactly zero. Not perfectly zero, but absurdly, improbably close to zero, off by a factor of around 10 to the power of 120 from what our best theories naively predict. This is the largest discrepancy between theoretical prediction and experimental observation in the history of science. Why is it so close to zero? If it were much larger in either direction, the universe would either have exploded apart instantly or collapsed immediately. The fact that it sits right in the sweet spot for cosmic structure to form, and for life to eventually emerge, is, to put it mildly, curious. Or take the ratio between the electromagnetic force and gravity. Electromagnetism is about 10 to the power of 36 times stronger than gravity. That's a 1 followed by 36 zeros, an almost unfathomably large number. And yet this specific ratio is precisely what you need for stars to burn steadily over billions of years, long enough for planetary systems to form, for life to evolve, for us to be here wondering about this. Physicists call this the large number coincidences, a cluster of seemingly unrelated physical constants that happen to align in exactly the right ways to produce a universe capable of complexity and life. The odds of this happening by chance in a single universe are, by some calculations, essentially zero. A programmer, of course, would just set those values intentionally. All right, let's get into the actual philosophical argument. The one that converted a lot of skeptics into people who lie awake at 3 a.m. thinking about this. In 2003, Oxford philosopher Nick Bostrom published his simulation argument. It's not a proof. It's not a claim that we are definitely in a simulation. It's something more unsettling. A demonstration that at least one of 3 propositions must be true, and that whichever one you pick, the implications are deeply uncomfortable. Here are the 3 options. Bostrom called them the trilemma. 1. Almost all civilizations at our level of technological development go extinct before they ever reach the ability to run detailed simulations of reality. Something kills them, war, climate, AI, some other catastrophe, before they ever get there. 2. Almost all technologically mature civilizations, the ones that do survive long enough to develop the necessary computing power, choose, for some reason, not to run simulations. Maybe they lose interest. Maybe it's ethically prohibited. Maybe simulations just turn out not to be interesting to them. 3. We are almost certainly living in a simulation right now. That's it. One of those must be true. You can't reject all 3. Think about why. If advanced civilizations are capable of running simulations, detailed ones with conscious beings inside, then there could be countless such simulations. Millions of them. Billions. Each one containing billions of simulated beings who believe they're real. Against that backdrop, the number of beings who exist in the one base reality is vanishingly small. The math says, if simulations are possible and anyone runs them, almost every conscious being in existence is simulated. The only escape is proposing that something prevents simulations from existing. Either civilizations always die first, or they always choose not to run them. But if neither of those is true, then here we are. Let's slow down and really feel the weight of Bostrom's logic, because it's easy to nod along without grasping how airtight it is. Start with a simple fact. You exist. You are a conscious, experiencing being. You are somewhere. The question is where, in base reality or in a simulation? Now think about the numbers. Suppose a sufficiently advanced civilization could run, say, 1,000 simulations. Each simulation contains billions of minds. How many minds exist in base reality versus simulations? One base civilization's worth versus 1,000 times that in simulations. Your odds of being in base reality, roughly 1 in 1,000. Now suppose civilizations can run millions of simulations, each with billions of minds. Your odds of being in base reality approach 1 in billions. And that's just from one civilization. If many civilizations across the universe reached this capability, the ratio skews even further. The universes running on simulated hardware vastly outnumber the one base universe, if any such universe exists at all. Bostrom's point is not that the simulation hypothesis is true. His point is that if you believe civilizations don't go extinct before reaching this capability, and you believe they don't universally choose not to run simulations, then the rational conclusion from pure probability is that you are almost certainly simulated. And here's the part that gets under people's skin. We have no strong evidence for option 1 or option 2. We don't know that civilizations reliably go extinct. We don't know that advanced beings would choose not to simulate. If we reject those 2 options without good reason, we're stuck with option 3. Now, to be fair, there are smart objections to the simulation argument, and we should take them seriously. The first major objection: we have no idea whether a simulation of consciousness is even possible. Maybe simulating a brain is not enough to create genuine experience. Maybe consciousness requires something, some physical substrate, some ineffable quality, that can't be reproduced in code. If that's true, the simulation would contain no real minds, and Bostrom's probability argument collapses. This is a serious objection, but it depends entirely on resolving the hard problem of consciousness, which we haven't done. We don't know what consciousness is or what produces it. Until we do, we can't confidently rule out the possibility that simulated brains have genuine experiences. The second objection: the computational cost. Simulating a universe at the quantum level, every particle, every interaction, every measurement, would require a computer of almost unimaginably vast scale, perhaps larger than the observable universe itself. But simulation theorists have a response here too. The simulation doesn't have to render everything at full resolution all the time. We already saw hints of this in quantum mechanics. Nature appears to be probabilistic precisely when things are not being observed. A sufficiently clever simulation might only render the parts of reality that are actually being interacted with and fake the rest. The third objection: this is unfalsifiable. You can't test it. It's not real science. That one's not quite right, and we'll address it directly in a later section, because scientists are actually trying to design tests for exactly this. Let's assume, just for the sake of exploration, that the simulation hypothesis is correct. Someone built this. Someone is running it. Who and why? The most straightforward answer in Bostrom's framework is a post-human civilization. That is, a future version of humanity or some branch of it that survived its technological adolescence, developed extraordinary computing capability, and decided to use that capability to run simulations of their ancestors. Why would they do that? The same reasons we do things with powerful tools. Curiosity, entertainment, research, preservation. A future civilization might run simulations of their evolutionary past the way we run historical reenactments or study ancient civilizations. They might want to understand how intelligence emerged, how civilizations rise and fall, what decisions lead to survival versus extinction. We are, in this scenario, a history lesson. Or they might do it out of compassion, an attempt to resurrect their ancestors, to give consciousness to beings who would otherwise simply not exist anymore. Something like digital heaven run as a program. Or, and this is the less flattering option, they do it for entertainment. We are, quite literally, characters in a game someone is playing. Our struggles, our wars, our loves and losses, content. Watched or not watched for amusement. The uncomfortable truth is that we have no way of knowing which of these motivations applies. From inside the simulation, the programmer's intent is completely opaque. We can only observe what the simulation seems to value, and it seems to value complexity, emergence, and conscious experience. Whether that reflects the programmer's purpose or is an accidental byproduct of good simulation design, we cannot say. There's an interesting taxonomy of what our simulation might be, and it matters philosophically even if we can't determine which category applies. If we're an experiment, then someone is watching for specific outcomes. There are variables being tested. Our choices as individuals, as a civilization, might be data points. The simulation might have run before with different initial conditions and might run again. We are replicated subjects in a controlled trial. If we're a game, then we might have a player or players who interact with the simulation. Some simulation theorists half-seriously suggest that moments of apparently impossible luck, against all odds survival, or history-changing interventions might represent the programmer adjusting variables. Every great miracle in human history might be a finger on a keyboard. If we're an ancestral simulation, then we are the past, a reconstruction of a civilization that actually existed, being rerun either for research or for the benefit of the simulated beings themselves. In this version, there's no external player. No one is watching us specifically. We're just running, doing what we do. Each of these scenarios has profoundly different moral implications for the programmer. An experiment treats us as means to an end. A game risks treating us as toys. An ancestral simulation is at least motivated by something like respect, a desire to bring back a world that was lost. Here's the part of this conversation that tends to make people very uncomfortable in very different ways, for very different reasons. The simulation theory is, in certain formulations, almost indistinguishable from classical theism. Think about what it proposes. There is an intelligence vastly greater than our own that created the universe. This intelligence designed the physical laws and constants. It may observe us. It may interact with us or choose not to. Our lives and choices may have meaning within some larger framework that we cannot fully perceive. Strip away the computational language, and that's basically what most major religions have been saying for thousands of years. Many simulation theorists are not religious and would resist this comparison. The programmer is not a personal God who cares about your prayers or forgives your sins. The programmer is an advanced being running a program, probably for reasons that have nothing to do with your individual well-being. But the structural similarities are striking. Religions have long described a reality that is not what it appears, a veil over true existence. The Hindu concept of Maya, the Gnostic idea that the physical world is a lesser creation, a kind of cosmic mistake. The Platonic notion that what we perceive are shadows of greater truths. These frameworks, developed entirely independently of modern physics and computing, map surprisingly well onto the simulation hypothesis. Some theologians find the simulation argument interesting rather than threatening. If God is the programmer, then the simulation isn't an alternative to religion. It's a mechanism by which God operates. The cosmological argument for God's existence, the universe must have a cause, and that cause must be something outside the universe, fits perfectly in this framework. The programmer is outside the simulation. Others find it deeply unsettling, because if the programmer is just a being, not omnipotent, not omniscient, but just very, very advanced, then the comforting certainties of faith are replaced by something much colder. We might matter to our programmer, or we might not. There's no guarantee either way. Here's where the simulation hypothesis crosses from philosophy into something that looks a lot more like science. Several research programs are now actively investigating whether our universe has the kind of signatures you'd expect to find in a simulated reality. These are real proposals taken seriously by real physicists. And while the tests are difficult and the results so far are inconclusive, the fact that they can be proposed at all is significant. The first and most discussed approach focuses on the idea of a computational lattice. If the universe is being simulated on a grid, like the pixels of a screen or the cells of a computational lattice, then there should be artifacts. At very small scales, the structure of spacetime should reveal a preferred direction, the direction of the grid. Energy limits, patterns that don't occur in a truly continuous spacetime but do occur in a discretized one. The challenge is that these effects, if they exist, would only appear at energies far beyond anything our current accelerators can produce. The Planck scale is roughly 15 orders of magnitude beyond what the Large Hadron Collider can probe. So right now, we literally cannot look that deeply. But the search for cosmic ray anomalies offers another avenue. Ultra-high-energy cosmic rays, particles traveling through space with enormous energies, might be affected by the structure of a computational lattice. If the universe has a preferred orientation at the Planck scale, very high-energy particles might behave slightly differently depending on which direction they're traveling. Researchers have looked for this effect. Results are suggestive but not conclusive. One of the most concrete proposals came from physicist Silas Bean and colleagues at the University of Washington in 2012. Their reasoning was elegant. We already simulate physical systems. Nuclear physicists simulate quantum chromodynamics, the physics of quarks and gluons on computational lattices. These are small, crude simulations by the standards of a universe simulating civilization, but they have a key feature. They produce artifacts. The lattice structure introduces subtle patterns, particularly in the distribution of high-energy particles, that are detectable if you know what to look for. Bean's team proposed that if our universe is similarly simulated on a lattice, it might produce identical types of artifacts. Specifically, the highest energy cosmic rays might show an anisotropy, a direction dependence, that reflects the orientation of the underlying computational grid. And here's the thing, we have detected something unusual about ultra-high-energy cosmic rays. The GZK limit, a theoretical energy ceiling for cosmic rays based on their interactions with background radiation, is real, but the distribution of cosmic rays near this limit shows features that some physicists find anomalous. Are these the artifacts of a simulation? The honest answer is we don't know. The data isn't conclusive, and there are conventional explanations. But it's a real, specific, testable prediction, and that puts the simulation hypothesis in a different category than pure philosophy. There's a deeper problem lurking behind all of this, and it's one of the most philosophically vertiginous aspects of the whole simulation debate. Even if we found compelling evidence of a simulation, lattice artifacts, computational limits, signs of external intervention, the programmers could simply patch the simulation to hide those signs. If they're sufficiently advanced, they can update the rules of physics from the outside. Any evidence we find, they could erase. Any test we devise, they could make pass. This isn't paranoid speculation. It follows directly from the structure of the scenario. If you have a sufficiently powerful simulator, you can make the simulation appear however you want from the inside. A simulation that wants to stay hidden can stay hidden, which means that, in principle, we might live in a simulation that is deliberately designed to be undetectable from within. No experiment we could ever run would reveal it. The simulation is perfect, and our science will always find a consistent, physical explanation for everything we observe. That's not the same as the simulation being false. It just means it's unfalsifiable. And unfalsifiability is normally the death knell for a scientific hypothesis. Karl Popper's criterion for science is that a theory must make testable, falsifiable predictions. A hypothesis you can't test isn't science, it's metaphysics. But here's the thing, so is the denial. Claiming with confidence that we're not in a simulation is equally unfalsifiable. We cannot rule out either option from within the system. That leaves us in a strange epistemological position. Not knowing is itself the answer, and it's an answer that cuts very deep. Let's say the evidence tips. Let's say tomorrow, a physicist publishes a paper with ironclad evidence that we are living in a simulation. The world absorbs this. It's confirmed. It's real. Now what? The first thing most people want to know is, does it matter? Are our lives less meaningful if they're happening inside a computer? Here's one way to think about it. Your emotions are real to you. Your loves, your losses, your ambitions, your regrets. You experience them fully. The fact that those experiences might be generated by code rather than neurons in a biological body changes their substrate. But does it change their reality? If you feel pain, you feel pain. If you love someone, that love is real to the version of you experiencing it. But free will gets complicated. If the simulation is deterministic, if all events are the unfolding of a program, then every choice you've ever made was predetermined by the initial conditions and rules of the program. You've never actually chosen anything. You've executed code. Of course, this is also a problem for purely physical theories of the universe. Classical physics is also deterministic. If the brain is just matter following physical law, then choice is an illusion in the physical universe too. The simulation adds a layer, but doesn't necessarily change the underlying dilemma. What it does add is the possibility of something more disturbing. The programmer could intervene, could rewrite your choices, could reach in and change what you do. In a simulation, free will might not be just philosophically uncertain. It might be actually and literally overridable from the outside. Someone could press a button and you would behave differently, and you would never know. The question of what it means to be real turns out to be harder than it looks. Most of our intuitions about reality are based on consistency. The world behaves the same way yesterday and today, and we can form reliable models of it. A simulation might produce exactly this consistency. And if it does, then from a functional standpoint, it is real. It's as real as anything we could ever have access to. Perhaps real simply means consistently experienced. In which case, simulation or not, what we have is real. Now we get to the question that hits people hardest. What happens when you die? In a simulation, that question has a new dimension. In a conventional physical universe, death is the end of the biological processes that give rise to consciousness. The brain stops, the pattern that was you dissolves, and that's that. Whatever continuity you experience during life, that thread cuts. In a simulation, it doesn't have to work that way. Your mind, your consciousness, your memories, your personality exists inside the simulation as data. Data can be saved. Data can be copied. Data can be restored. From a purely technical standpoint, there is no reason why a sufficiently capable programmer couldn't store the state of a mind at the moment of death and reconstitute it later. In a different context, a different environment, or simply resumed where it left off. This isn't guaranteed, of course. We have no way of knowing whether the programmer does this, or cares about individual minds, or even notices when one stops running. The programmer might be running the simulation for purposes that have nothing to do with the well-being of the beings inside it. But the possibility is there in a way that doesn't exist in a purely physical universe. Death in a simulation need not be permanent. It might just be a state change. Many religious traditions have described something like this for millennia. The soul persisting after death, resurrection, reincarnation, the idea that the thread of consciousness doesn't cut but continues in some other form. The simulation framework doesn't validate any specific religious tradition, but it does provide a technological mechanism by which these outcomes would be possible. Some people find that deeply comforting. Others find it more disturbing than straightforward oblivion, because it raises the question of what the programmer does with those stored minds, and whether the answer is something you'd want. And now, the final question, the one that actually matters. How do you live knowing that you might be a character in a program? There's a temptation, and some people do fall into it, to respond with nihilism. If nothing is real, nothing matters. Effort is pointless. Relationships are simulations of relationships. Love is an algorithm. Why bother? But this conclusion doesn't follow, and it's worth being clear about why. Your experience of effort is real. Your experience of love is real. The fact that these experiences might be generated by a simulation doesn't make them less real to the being having them. The simulation doesn't subtract from your experience. It just adds uncertainty about the metaphysical substrate of that experience. Think of it this way. Even in a physical universe, your emotions are just electrochemical signals in your brain. Does that make them meaningless? Of course not. The mechanism doesn't determine the meaning. You determine the meaning. Many philosophers argue that the simulation hypothesis actually enriches how we should think about ethics. If we might be simulated, if our experiences might be data in a larger system, then questions about what kind of experiences we create for ourselves and others become even more urgent. We are potentially generating data. What kind of data do you want to be? There's also something quietly empowering about the simulation framework. In any great simulation, the interesting parts aren't the background, the static trees and the empty streets and the unchanging backdrop. The interesting parts are the beings who do unexpected things, who make choices the programmer didn't anticipate, who create, who connect, who surprise. If we're in a simulation, the most meaningful thing you can do is be interesting. Be real in the fullest sense, fully experiencing, fully choosing, fully engaged with the extraordinary strangeness of existing at all, whether or not someone is watching. Because if there is a programmer, and if they have any aesthetic sense at all, they are not watching the beings who gave up. They're watching the ones who kept going. We started this video with a simple observation. Everything around you feels completely real, and it still does. That hasn't changed. What has changed, or what I hope has changed, is the context in which you hold that feeling. Because we've seen that feeling real is not the same as being base reality. That the mathematics of our universe, the behavior of quantum particles, the philosophical logic of probability, the strange anomalies that science can't fully explain, all of them point, at minimum, to a question worth taking seriously. Are we living in a simulation? The honest answer is we don't know. We may never know. The question might be permanently beyond the reach of any test we can design. But here's what we do know. We know that the universe is stranger than our intuitions suggest. We know that at its smallest scale, reality behaves like information being processed. We know that the fundamental constants of physics are calibrated with improbable precision. We know that observation changes quantum outcomes in ways that still have no satisfying physical explanation. We know that a logically rigorous argument, one that hasn't been defeated despite 20 years of attempts, puts the probability of being in a simulation uncomfortably high. And we know this. Whether or not we're in a simulation, we are here. We are experiencing something complex and beautiful and terrifying and brief. And that experience, wherever it comes from, is ours. The simulation hypothesis is not an invitation to despair. It's an invitation to wonder, to look at the stars and ask not just what are they made of, but what are we? To look at the quantum strangeness of the subatomic world and feel the floor of certainty shift beneath you, and find that unsettling, yes, but also thrilling. Because if there's any chance that we are conscious processes inside an unfathomably grand computation, then the fact that we can ask that question, that we can run the math, read the philosophy, build the experiments, feel the vertigo, is extraordinary. We are, perhaps, the simulation becoming aware of itself. And that might be the most remarkable thing in any universe, real or otherwise.